the different classes of enzymes. And how there's that the Enzyme Commission has 6 classes that they use, almost like a social security number for an enzyme, but that there are subclasses and some are common names. So you should know the family names of the enzymes, especially for next semester. It will make your life so much easier, at least by 1/2, if not more, if you know the family names, because then you can get a decent chance of knowing the enzyme for the metabolic pathway and understanding the reason why it works the way it does. But there were the oxidoreductases, which are the redox reactions, which is the transfer of electrons. I don't know why that does that. No. The transferases, which transfer groups, functional groups. Hydrolases, which use water. Sometimes it's a condensation reaction. Sometimes they're named for the backwards reactions from the way that they were discovered. But there's waters involved, either being hydrolyzed or condensed. The lyases, which either add or remove groups using double bonds. Isomerases, which sometimes are also called mutases, which go from different stereoisomers to each other. And then ligases create the new single bonds, coupled to like ATP or NTP or something like that. So that was, and that similar cofactors like that. Okay. This should just be a review. Is that normally anytime you have a reaction taking place at constant temperature and pressure, which is important, which is usually what we're talking about in the body, we're very limited. Due to homeostasis, we're very limited to the temperature and the pressure controls. So then you can calculate the free energy as delta G is equal to delta H minus T delta S, which we've already covered earlier this semester. And that you get this delta G is equal to, under standard conditions, remember biochemical standard conditions are a little differently than those from Gen Chem, where it's at 37 degrees and pH 7 and 1 millimolar magnesium chloride, that you get delta G is equal to minus RT ln of the equilibrium constant. Okay, so that should be anything new. And what should also be true, or what it's not should be, it really is true, is that you have that energy profile where free energy, or E, you would always have every reaction. Now this one shows it being, one that would be exergonic, meaning that would be spontaneous and going from substrates, or A, to product B, and it's lower in overall energy. But you always have to add energy, and so every step of a reaction has to have a transition state, which is that hill, the hill part of it. Okay? All right, and this activation energy right here is the hump that you have to get over. And so what happens here is that, and I want to point out, is that a catalyst, which all an enzyme is a catalyst, is that all it does is it lowers that hill. It does not change the equilibrium constant at all. Equilibrium constant is always products over reactants, and you still have the same concentration of products and the same concentration of reactants overall in the end. And it lowers the backwards reaction just as much as it lowers the frontwards reaction. So the same order of magnitude here has been affected. Oops, let me change the color. So this is still the same order of magnitude whether you're going backwards or frontwards. Okay. So all it does is the catalyzed reaction has brought that what had been a big hill down to a much smaller hill. Okay. But the overall delta G free energy change for the entire reaction is still the same. Okay. So that's how the rate is increased, is by the lowering of that energy. Now this one shows it as binding energy because we only have one step. Okay, I just wanted to point that out because in some mechanisms there's more than one step, and so therefore it may be that the biggest hill or the biggest hurdle was not the first one. It could be a second or a third step. And whatever the enzyme does is that it lowers whatever had been the rate limiting step to a much more manageable position. Now this next graph. I think it illustrates a good point, but I also don't like it as well because it makes certain assumptions that are not always true. So before I even do that, I want to just go ahead and explain a little bit. Okay, so what we have is you have in the simplest case, well, in a simple case, we have an enzyme plus a substrate, and you have to bind. Okay. Typically, binding is reversible. Not always, but typically it is. That's why we have it going frontwards and backwards. And you make what's called the ES complex. This also has a special term. It's called the Catalase complex sometimes. And you'll find out the reason why is because of the whole idea of the Michaelis-Menten equation. It's called the Michaelis complex. Now, I'm showing it going frontwards and backwards, but not all enzymes can go both frontwards and backwards. You can get where it turns it into the product, and then you can get product release, because you have to get your enzyme back, or otherwise it was a substrate to begin with, it was a reactant. And the Michaelis complex only refers to this part right here. Now, one other thing that they do in enzyme kinetics is, remember, a lowercase k, if it's a lowercase k, that's a rate constant. So that tells you speed, but it doesn't tell you equilibrium. Capital K's are equilibrium. That tells you overall, will it favor products or will it favor formation of substrates. Now, what they do if you start to read some of your papers on your enzyme, and they start talking about rate constants and things like that, one thing that they do, which at first may seem daunting, but it starts to make sense later on, is they give each reaction, it's a lowercase k, because each one's going to have a speed, a rate constant, and they give it a subscript of the number of the step that it is. So for example, this is k1, lowercase k, 1, and when it goes backwards, it's lowercase k subscript -1, because it's going backwards of the first step. So the second one, in this example here, going from ES to EP, would be lowercase k2. If it was able to go backwards, it'd be lowercase k -2. Same thing here, k3 and lowercase k -3. Just like the equilibrium constant is the ratio of those. So for example, the equilibrium constant for that very first one would be k -1 divided by k1, because this is the ratio. Okay, so for example, you just say KEQ of step 1 would be equal to lowercase k -1 divided by, because it's products over reactants. And I could mathematically show you how that is true if you want me to do that at some point in time. I won't do it right now, but we can at some point in time. And then same thing for KEQ for the second step would be k -2. I mean, whoops, this should be K1. K1. Sorry about that. For the second step would be k -2 divided by k2, and third step would be k -3 divided by k3. I wanted to point this all out because of this next graph that it's going to show. Okay. So here we have in the black the regular uncatalyzed state. And then what happens is once the enzyme is involved, we're going to get that ES and EP. So we get the Michaelis constant complex, and we get the EP. And we still are going to have transition states. What I want to point out that I think that they have oversimplified is that here, unfortunately, they show all of the hills, all of the steps about the same. And that's not necessarily true. And they show that all of the valleys are the same. That's very, very rarely true. Okay? But I also want to point out that the way it catalyzes is overall the biggest hill is no longer as tall as what it had been before. But it could also look something like this. And for every step, you're going to have a hill, a maximum, and a valley, a minima. Okay? So for example, we could say that it's binds. There's the ES complex. But the EP And then we get the P right back there again. So they don't have to be the same height, they don't have to be the same depth. And that could also tell you which of the complexes, of the enzyme-bound complexes, is more stable than the other. Is ES more stable or is EP more stable? No, it's going to be EP because it's the lowest one in energy. The lower you are in energy, the more stable you are. And so, see, this one here for EP is lower than the one for ES. But you always have the transition state for binding. The binding is that first step when the enzyme becomes substrate. Then we have the catalysis. Catalysis here is ES going to EP. That's whenever the chemical step, some people call that the chemical step. And then the release is EP going to E plus P. So now in this reaction mechanism, what is the rate limiting step? We have three possibilities before you think about it. We have one possibility is binding, and the one was this red. The second possibility is, I'm going to call it chemistry, which is ES becoming EP. And the third possibility is product release. Because those are the three steps here in this enzyme mechanism. And sometimes you can easily tell, sometimes you can't easily tell, but I would expect you to be able to explain the logic used. How can we tell, before we say which one is the answer, what makes a rate-limiting step the rate-limiting step? It's the slowest. And what makes it the slowest? Think about it, you're on your bicycle, pedaling along. What makes the slowest or the most difficult step or leg of the one that takes the biggest hill to climb? And so what you need to do, in this one, unfortunately the way I drew it, it's kind of difficult, is this the highest hill, the first hill? Is it the second one, just going from the ES to the top, or is it going from the EP to the top here? And here probably, they're all about the same, but maybe the EP to that third hill, maybe the highest hill to climb. And if that's true, then that would be the rate limiting step. And so, let me do another example. Where it makes it a little bit more obvious. So like in this example, whoops, that P, it should end up where the P ends, is not above it. But this one's clearly, the third step is going to be the rate limit. It's still catalyzed because the overall hill is, see, the uncatalyzed hill is taller than that third one, but that third hill is going to be going from EP to just P alone. That's the biggest hill that you'd have to ride your bike up. And so that's the rate limiting step. It's not always product release. I just wanted to show one that was really, really obvious. And the reason why is going to be because in a moment when we start talking about the way that enzymes work. Okay, so you always look to see what the biggest hill to climb is, because that will be your rate limiting step. So the way that enzyme catalysis works, there are two models that are on the extremes side. And we've already discussed this in many ways. There's the one that was the original one, which was called lock and key. And that's because the enzyme would have a binding site that is complementary to the shape of the substrate. So the substrate just fits right on in, and that's how it works. All right? And it doesn't take into effect the fact that both proteins and if it's a nucleic acid, because not all substrates are proteins. Most enzymes are proteins, or some of them are nucleic acids, but a protein can act on anything. They can act on sugars, they can act on other proteins, they can act on nucleic acids. There's lots of fats, lipids, lots of things that they can act on. But they don't take into account the fact that the enzyme itself could be flexible, and also that the substrate could be flexible. And then there's the induced fit model, which was that the binding of the substrate induces a change in the shape of the enzyme that results in a complementary fit. And so, your book, and I'm going to break it down, likes to use this figure. And delta GM, by the way, is the difference between the transition state of the uncatalyzed versus catalyzed reaction. But I'm going to show each of these in their own right. Because at first it took me a little I mean, I had to look at this a time or two myself to understand what they were trying to say. They said, suppose that you have a reaction which is just a decomposition reaction where you're taking one thing and you're breaking it into two. So they say, oh, we have a metal stick, and then our product will be a broken stick. So you're going to have two pieces of a broken stick. And so that transition state, you can imagine just bending it. And so if it's uncatalyzed, it looks just like what we've been talking about with S going to P, and you have that transition state. If it's a locking key, remember that mechanism or that model suggests that the binding site for the substrate is complementary to the shape of the substrate. So that means it would look just like that stick or that metal rod. And what they're saying is, imagine that the reason why it would be attracted to each other would be because it was magnetic, and so it would just fit right in. The problem with that is it would stabilize that interaction. It would be happy there. It's all nice and snug, all cuddly, and so it would actually be worse than what you started off with because it stabilizes the ES complex too well if it's complementary to itself. Or if you don't like the magnets, you can think of it as ionic interactions. If the substrate was positively charged and the binding site of the enzyme was completely negatively charged and the same shape, then it would just get in there and it gets stuck. Okay? And so by doing that, it actually stabilizes this ES complex so much to where now the hill to climb up is actually bigger than the original hill was. And so that's why chances are the lock and key model is not adequate in explaining what happens. So instead, we have this idea of an induced fit, or the idea that it's called transition state theory, which I don't know why it's a theory, but I mean, well, it's a theory because they say it's not a law yet, but that most enzymes, instead, what they are is they're more complementary to the transition state. And so that way, when the substrate starts to bind to the enzyme, it makes that transition state, which makes it so much easier to break in this instance. And so it stabilizes, instead of stabilizing the ES complex, it's going to primarily stabilize that transition state. And so that's why the transition state actually decreases in energy. Now they're showing how ES is exactly the same energy as S. Well, that's not necessarily true. Okay, like it could be a little higher, it could be a little lower. But what a transition state theory states is the fact that what gets stabilized is the transition state. So doing that lowers that energy, and it makes it easier. If you've already bent that rod, it makes it so much easier for it just to go ahead and snap. You want to think of it like that.
What did you say that theory was?
This is called transition state theory. And it's the prevailing theory. And they know that it works for, a number of enzymes. My poor stylus, like the little rubber ball part on it, it's about to rub off. Okay. All right, and so this is just an example. This is catalase. And what happens is if there was absolutely no catalyst, and they just said that the relative rate was 1, which in reality it's actually, I thought this was one of the fastest ones, but it's actually quite slow. You can do this if you think back to organic chemistry. A lot of these reactions, remember, you used to use platinum, palladium, nickel, and rhodium as a catalyst. Well, you can use platinum actually as a catalyst for the catalase reaction, and it increases it 10 to the power 4, which is what, 10,000, so like 27,000-fold. But catalase actually causes that activation energy to become even lower, and it does it to 6.5 times 10 to the power 8-fold faster than without the catalyst. Okay, under those standard biochemical conditions. And so this just shows you some of the examples of rate. Carbonic anhydrase is one that we've talked about. That's why it helps control your blood pH. It makes the carbon dioxide in your blood soluble. It's 10 to the 7 power fold. TPI, which is one that we will talk about a lot next semester, which is triose phosphate isomerase. So what kind of reaction do you think will that one do? It changes between different isomers, stereoisomers. sugars that have 3 carbons and 1 phosphate. And what it does is it moves the phosphate from carbon 1 to carbon 2 and vice versa. Carboxypeptidase actually breaks off, chews up proteins from the C terminus. Phosphoglucomutase is one. It's another isomerase, because mutase is just another one, and it's in glycolysis as well. Phosphoglucomutase is, and it goes to 10 to the power 12-fold increase. And then succinyl-CoA transferase. What kind of reaction is that one? It's the transfer group, and it's 10 to the power 13-fold urease, and then aridine monophosphate decarboxylase. And so, what do you suppose that one does? If it's a decarboxylase. It gets rid of a carboxyl group. It gives off CO2. Okay. Yep. And then it's 10 to the power 17. All right. This should make sense. I mean, kind of logical sense. There's an optimal temperature. And so you can imagine that this is just an example. At really low temperatures, the enzyme may not be very active. You increase the temperature, the activity will go up until it gets to the optimum temperature for that enzyme. And then the enzyme activity is going to go down until where at some point in time you'll get so high temperature that chances are that it should abolish all activity. What happens at the really high temperature? What happens to the enzyme? It denatures. So that's why, but there is an optimal temperature. And it may not be 37 degrees. It may be something higher or something lower. Okay, but there is an optimal temperature. And so that's just what that's all about. Okay. And so we have different types of catalysis. Many enzymes use what they call a binding energy in order to form the Michaelis complex, but that's not the only way, okay? You can either also do it to where you have the functional group that's going to be the nucleophile that does the attacking, or you can even have like metal ions or metal activated water ions that's available to do the attacking, that's already positioned in the right location inside the enzyme's binding site. Okay? But many times there's also a covalent interaction where the enzyme literally forms a bond with its substrate or product, and then it has to be released later on. Okay, because it has to be transient, because otherwise the enzyme would be permanently modified and it would then no longer be a catalyst. It would have been one of the reactants in the original reaction. And so there are 3 broad types of catalysis. There's one called general acid, general base. And actually, there's something called specific acid or specific base, but a specific acid means that it's literally a proton or a hydroxide anion that does the reaction. Okay, so it only uses water. That doesn't happen a lot, because a lot of times the proton or the base is something that's associated with one of the amino acids. Okay, and so if it's that way, then it's called general acid, general base. So some of the amino acids that are really important for general acid, general base reactions, obviously like aspartic acid, right? Because it's a carboxylic acid and a carboxylate. Glutamic acid. You could also have histidine. Histidine's really good because it can act as both an acid and a base, an acceptor and a donor of protons. Even lysine, arginine, serine, threonine, tyrosine, all of those that have those protons. Cysteine is actually a really good one, where it can either donate a proton or accept that proton back. Those are often utilized in general acid, general base catalysis. And if you have a general acid, you're going to have a base, because it's like a yin-yang, since it has to be reversible. Okay. Whereas covalent catalysis means that you form an intermediate where what had been the substrate is literally covalently bound to the enzyme complex. And then another nucleophile comes in and knocks it off. A lot of times that nucleophile will be a water, but not necessarily. It could also be like an acyl group. So we'll talk about that. Or it could be a carboxyl group, for example, with aminotransferases. They form what's called a Schiff base, which is a covalent intermediate. And then finally we have metal ion catalysis, which is where a metal ion or a metal activated water is utilized to do catalysis. Okay. And you can even have two different types occurring within the same enzyme. It's not all or nothing. Okay. You can have something acting like a general acid that helps make a metal activated water or metal activated hydroxide that does the attacking, and so on and so forth. All right, this should be a review from like Gen Chem 2. And that's the enzyme kinetics, like the rates of a reaction. You can either think of it as, so rate, which they just put as an R, but a lot of times we use V or nu for velocity. It's either going to be equal to the disappearance in a substrate or the appearance of product, whichever is easiest to see, right? So it's why we get, and this right here, like the change, remember the delta means change of A with respect to the change in T, that's really calculus, okay? I don't know why. If we put a triangle there, the delta sign, people are like, oh, okay. But that's the exact same thing as a derivative. Minus dA dt. That's the exact same thing. Because that d just means a delta for change. But I don't know. When I was in calculus, they didn't ever really point that out. It seemed much more daunting if it was a d versus a triangle. But it's the same thing. So I'm just saying that just in case you see that in some of your papers. Or if I accidentally write it as a d instead of a triangle. And it's negative because it's disappearing, which makes sense, because the substrate's disappearing. B, the rate. Since it's a coefficient of 1 to 1, now if it was a coefficient of 1 to 2, then B would be disappearing twice as fast, right? Because it's for every 1A, 2 B's would be disappearing. Or if it was 1 to 3, then for every 1A that disappears, 3 B's would disappear. But product is appearing, so that's why it's going to be positive. It's a positive change. Okay, let me erase all those. And then this is just your rate equations from, and I don't know why they put the letters F and G. F is just the coefficient here. G would be the coefficient for B. Usually we use like X and Y. I don't know why they liked F and G in this one. But we have rate, which once again would be V, is equal to whatever that little rate constant was times the concentration of each substrate to whatever, in this instance, whatever coefficient it was in the balanced equation. That's for the formation. That's going to be equal to the change of P with respect to time. Oops, my P didn't come out well. Okay. So, then we had this idea of orders. So let me just go on. So I have a good PowerPoint for it. So for example, if we had just A goes on to make some product, I'll say P for product, then the rate would be equal to V, which is the rate, would be equal to K times A. This is called a first order rate constant, or first order rate. And the reason why is because it's to the 1 power, right? Because the 1 is implied. So that means if you double A, you double V. If you triple A, V gets tripled. Now the units for K change with respect to whatever order rate it is. Because the units for V never change. It's always some type of concentration. Many times we talk about molarity, like molar per second. Or it could be, sometimes they can give rates in really, really weird, especially in a lot of biology, more of the biology papers. Because they'll say like milligrams for, like because it's a concentration. So milligrams per milliliter per second, or milligrams per milliliter per hour per day. I mean, it's just some random kind of thing. So you have to be kind of careful. But biochemists usually stick to some type of molarity. Sometimes it's like millimolar. And then, of course, the units of time would be seconds or minutes or something like that. And the concentration, and an A is always in concentrations, like molarity. So that means that the K in this instance would be in inverse seconds. That would be its unit. Because it would have to be in inverse seconds in order for V to equal to molar per second. Like that's just the default. But that's a first order rate constant. A second order rate constant, there are two ways for you to have a second order rate constant. You could either have two A's going on to make P, because now it's going to be second order with respect to A, because it takes two of them to make P. Or you can have A plus B goes on to make P. Both ways, you would have a second order rate constant. I'm going to just write the equation for the second one that I did up there. But we'd have V is equal to lowercase k, of course, times A times B. So it's first order with respect to A, because that's first order with respect to B, but second order overall, because you just have to add them up. 1 plus 1 is 2. And then we do the units. The units here for V is always going to be some type of concentration per unit time. So once again, I'm just saying molar per second. And then A would be in molar, B would be in molar. So what would K be? Well, K has to have an inverse second in there, because you have to have a second on the bottom. But how do we get rid of one of the M's? So it's per molar per second. That's the units for K. So that way you have an M to the minus 1, cancels out one of the other M's. That's the minus 1. So that's second order rate constant. And you can actually have something called a zero, which I do have a slide for a zero rate constant. But a zero means it's not dependent upon any substrate concentration. I can't draw it out like this, but it'll make sense once we start doing our standard steady state conditions. Because at some point, well, I'll just explain at some point in time. But there's something called a zero. And then if a zero rate constant, the unit for it would be molar per second, because everything else is to zero power, which is 1. Once in a while you'll have it's called a termolecular. That means it's got 3. It's a third order rate constant. But for enzymes, almost always we're talking about either 0, first, or second order. Okay. And so, yeah, the rate constant is just a proportionality constant. It gives you an idea of how fast something goes. And then the order of the reaction is just the sum of all of the exponents. And it helps you understand the mechanism. All right. Alright, so like in this instance here, it says it's first order with respect to A, first order with respect to B, second order overall. And then we give just an example. This is a glycogen phosphorylase, the enzyme. We actually talk about it next semester. So the rate is equal to rate constant, of course, times the concentration of glycogen times phosphoric acid. Okay. So a zero order rate constant means it's at a constant rate. So you can keep adding more and more substrate, it will not get any faster. Okay. So the rate is independent of whatever the reactants are. And we will see this whenever you get the concentration of the substrate so high that all of the enzymes are already busy. So that means, this is a very, very simplified example, but let's say we have 5 enzyme complexes and you add in 7 substrates. all 5 enzymes will be bound and be working, and you're going to have 2 left over. So you can keep adding more and more and more, but until they are finished with one of the 5 at least, it's never going to be able to go any faster. And so that's why it's called saturation. It's saturated. All of the binding sites on the enzyme, or all of the enzymes present, are completely full. And so then it becomes 0 order. And I've actually already used this, but this is just to reiterate. Substrate is the letter S. That's just a reactant for an enzyme. The active site is the part where the chemistry occurs. Usually it's non-covalent, but it can be briefly covalent as long as it's released. And the ES complex is also called the Michaelis complex. So we're going to look at a very specific example now. It's called aspartate transcarbamoylase, which is a mouthful. They abbreviate it as ATCase. This is carbamoyl phosphate. And one thing, this is just like an acetyl group is a methyl with a carbonyl. A carbamoyl group is an amino group with a carbonyl. So it's an amide. It's the simplest amide. Okay? So that's a carbamoyl, and then phosphate is just phosphate. And this is important for DNA and RNA synthesis. And you take it, you add in aspartate, ATCase takes over and makes N-carbamoyl aspartate and gives off the hydrogen phosphate. But if you look at the velocity as a function of substrate, we see something. First off, there's what's called the maximum velocity. They abbreviate and they call this Vmax. Whoops, that's supposed to be a big V subscript max. Because you can never get faster than that. At this point in time, it's now 0. Whoops. At this point in time, it's now 0 order. Because you keep adding more substrate, it doesn't matter. Okay. Now, if you notice, ATCase is sigmoidal. So if you think about where have we seen that sigmoidal shape before? Hemoglobin binding. Okay? And so what does that mean? It's cooperative. This is a cooperative. And so it has cooperative binding just like hemoglobin. And so it's called allosteric or allosteric interactions. Not every enzyme is cooperative like that, and I have to tell you, it makes the math much more difficult when it's cooperative. Much more difficult. If you get something that's not allosteric, then it's much more simple. Okay. So this is just a generic rate. So we have some just random enzyme, and it's important here that I want to point out that they do what's called initial velocity. And that's because if we just think about it, and this is time. This time I'm not talking about substrate concentration, and we talk about the amount of product, which is actually how you find velocity, right? Velocity is the change in product with respect to time. Well, at time 0, there's no product because the reaction hasn't started yet. But then at first it's going to go up really fast, right? Because that enzyme's working overtime, so to speak, in order to make product. But then it's going to start to slow down, until at some point in time it's going to completely peter out because you've made all the product you can make. You used up all your substrate. So velocity is a derivative, right? Because it's the change of product concentration as time changes. And if you think back to calculus, see the tangent here, the velocity there is a lot different than it is here. And up here, it actually gets to 0. And so you have to define where you want to talk about your velocity. And so they always do it at this end, what's called the initial velocity. Because that's what you always compare all enzymes with, is your initial velocity. So anytime from now on, whenever we talk about V versus S or Michaelis curves or anything like that, they're always talking about the initial velocity. Because otherwise, at some point in time, the velocity is going to approach zero. It's a limit. Okay. So the easiest one to point out is this: at this end, when you get to really high substrate concentrations, it's zero order. No matter how much more substrate you add, it's already saturated. All the enzymes are busy. Whereas down at this end, in an ideal situation, it is first order. Okay? And if that's true, then it's called, they say that it follows what's called Michaelis-Menten kinetics. Okay, and that's what this little box there is saying. Okay, so now not every enzyme like ATCase doesn't follow Michaelis-Menten kinetics. So at the very, very low substrate concentrations, it is not necessary. It's not first order. But if they do, if it's a true hyperbola, truly hyperbolic, like this, then this region right here does follow first order kinetics, and this region up here follows zero order kinetics. And that becomes really, really important in doing what's called the Michaelis-Menten model or Michaelis-Menten kinetics, which is which is a simplification of the math. Just because something's been simplified doesn't necessarily mean it's easy. It's just easier than what it would be otherwise. So I'm going to end right there because I actually will sit down and derive Michaelis-Menten for you, because your book kind of skips around and assumes that you can figure out the math all in your head, and that takes some time and some thinking to do. So I'll go ahead and I'll end class with prayer.